Today we're going to learn how to draw Lewis structures. And Lewis structures, they basically represent how the atoms in a molecule could be arranged. In order to do so, we have to follow a couple simple rules, and I'll show these through a few examples for you. First, we're going to do formaldehyde, which is CH2O, meaning there's one carbon, two hydrogen, and one oxygen present in the molecule. The first thing we're going to do is write the chemical symbols for the elements, and we're going to place the element with the lowest electronegativity in the center, with the exception of hydrogen, because hydrogen will always be a terminal atom since it can only have 2 electrons in its outer shell and form only one bond. So we'll put the carbon in the middle, and we'll have the oxygen and 2 hydrogens surrounding it. Then what we're going to do is count up the total number of valence electrons. In this molecule, you have carbon, which has 4 valence electrons because it's in group 4. Hydrogen with 1, you have 2 of those, so that totals 2. Oxygen's in group 6, so that has 6 valence electrons, you have 1 of those. So now we have 12 valence electrons to work with, and what I'm going to do is draw bonds, which are a sharing of 2 electrons to connect all of the elements. In doing so, I've used up 6 of those valence electrons, and so I have 6 electrons remaining. Now what I'm going to do is satisfy the octet rule for the perimeter atoms, and hydrogen's already all set. Oxygen needs 6 more electrons to be complete, and that works out since we have 6 electrons available. Now what we have to do, oxygen's satisfied, however, carbon only has 6 electrons around it. So what we're going to do is we're going to form a double bond between the carbon and the oxygen by taking 2 of the unshared electrons on the oxygen and sharing them with the carbon. This will allow for a complete structure where you have all atoms satisfying their octet rule, hydrogen again only needing 2, so it's all set. Now, if we had some electrons left over, which we did not, we would have placed them on the central atom, and that's what's going to happen in this molecule. When we draw ammonia, nitrogen is the lowest electronegativity besides hydrogen, so that will go in the middle. And what we're going to do is we're going to draw bonds to connect the hydrogens to the nitrogens. We have 8 valence electrons with which to work. As I draw the connections, I use up 6 of those electrons, leaving me with 2 more. Now, since I don't need to place any electrons around the hydrogens to complete the octet rule, I'm simply going to place them on the nitrogen. Now I've used up all of the electrons, I have none remaining, and we have a molecule where all the atoms are happy and they're all set. Now, a more complicated polyatomic ion would be sulfate. Sulfate contains 1 sulfur and 4 oxygen atoms, but it's also a polyatomic ion, meaning it's basically gained 2 electrons to get its -2 charge. In addition, this has another problem because when you draw it, it's going to seem like it's correct at first, but then there's one last step that we're going to have to do for it, and that's called minimizing the formal charge. And we'll get into how that occurs. So first, I'm going to draw the elements. Sulfur being the lowest electronegativity, so I'm going to put that in the middle and surround it by 4 oxygen atoms. Then we've tallied up the number of valence electrons, so we have 6 from sulfur, 6 times 4 for the oxygen, which is 24, and then 2 electrons because of its charge. So a total of 32 electrons, and in drawing our connections, we're going to use up 8 of those electrons. So now we will have 24 electrons remaining. Now, since oxygen, they all need 8, and so they basically need 6 more. That works out because you have 24 electrons available. So if I put 6 electrons in pairs around the oxygen atoms, I will satisfy all of their octet rule. Now, this looks like it's happy and complete because sulfur also has a completed octet. However, what's going to happen is when we look at the formal charges of the atoms here, you're going to see that you're going to have positives right next to negatives. And when that happens, that puts a strain on the molecule, and it's going to cause the electrons to want to shift to alleviate that strain. So what we have to do is look at the formal charges of the elements present. So for sulfur, what we're going to do is we're going to take the group number, we're going to subtract the number of unshared electrons, and 1/2 of the bonded electrons. Remember, the electrons in a bond are shared, so we basically consider 1 going to each element. So sulfur, group number is 6. We're going to subtract, it has no unshared electrons, but it has 8 electrons involved in bonds being shared around it, so it gets 1/2 of those. So 6 minus 4 gives you a +2 formal charge. So Now, all of the oxygens are the same, so I'm just going to look at one, and we'll calculate the formal charge on that one. The oxygens, group number is 6 as well. However, you have 6 unshared electrons, and you have 2 that are involved in a bond, 1/2 of it belonging to the oxygen. So 1/2 of 2. So you have 6 minus 7, or -1. So each of the oxygens has a -1 formal charge. And that is not really that stable. So what's going to happen is, in order to alleviate some of that, 2 of these unshared pairs can actually be dropped in as multiple bonds to alleviate that strain. Now when we look at the sulfur, we're going to see that it's in group 6, and it's sharing 12 electrons. So half of them belong to it. 6 minus 6 is 0. So the sulfur now has no formal charge. If you look at the oxygen has 4 unshared electrons, and it's sharing half of these 4 electrons. So that gives it a formal charge of 0 as well. So we've minimized the formal charge, and the sulfate polyatomic ion breaks the octet rule. Now, we'll get into this in a later episode, but sulfur in any element on the 3rd period of the table or lower has the capability of doing that because it can hybridize using its D subshell. All right.